we are going to build digital timer on FPGA board, but unfortunately you don't have an FPGA board, so you will complete the project and simulate it. And don't forget the UCF file. Almost half of the students did not put it. Even I asked it in different timing, like during the lecture, in my announcement, and when somebody asked through email, I mentioned that please UCF is must, because what is there to grade? Just a circuit and UCF file and the word file. There's nothing else to be graded. So I need UCF file. It is must. And today again I announced this, so please don't forget. And some people did the mistake that I mentioned so many times in the class, that every file should be in the same folder of the project. Now some student put this debounce and the 7-segment file somewhere else. When they submit the project, they send it without those two files, because that was not in the folder, that was outside the folder. So this is a big mistake that I am mentioning. Please don't do it. Even then people are doing this mistake. So don't do this mistake, please. All the files are must. All the files are needed. Okay, now today we are going to have this experiment. Let us start. The objectives of today's experiment is what? Design modulo counters. You already have seen counters. So this is modulo counter. If you don't um, understand or you don't get my voice, just tell me, interrupt me, okay? Don't wait. So you already know what are the counters. Today we'll see what is the meaning of modulo counter. We already have seen modulo counters before, but we'll make our own modulo counter. Next objective, let me start the recording also.
It's already recording, Doctor.
Somebody already recording?
Yes.
Okay, good. So let us go forward. Then we will see what are the cascaded modulo counters to build a digital timer. Cascading means what we'll see. Next objective, generate slower clock signals from faster one with exact frequencies. If you remember in the last experiment, we did it. We generate the slower frequency from faster one. Faster one was the onboard clock, which was 100 megahertz. And we got 1 hertz, almost 1 hertz from that. But if you know that it is almost, it was not exact 1 hertz. It was 0.745 hertz, right? So if we use that frequency using digital clocks or digital timers, the time will be wrong, which is not good for these type of circuit. For counters, that's just to see the output changing at a slow frequency, or some other circuits which are not related to time too much. So that type of technique is easy and can be used. But if it is a digital watch or digital timer, we need exact 1 hertz. We cannot bear that thing. So we need exact frequency. Today we will learn how to get this exact slower frequency from a faster one. Okay. And we are going to make a digital timer today, which is like a clock or digital watch. It is very interesting experiment. You are going to build a digital watch today. But the problem is what? On our 7-segment display, we have 4 digits only. We need actually 6 digits. 2 for hours, 2 for minutes, and 2 for seconds. So due to this limitation, we will use the available 4 7-segment displays on the board. And what we will do, we will just display minutes and seconds. 2 for minutes and 2 for seconds. You need 2 digits for minutes and 2 digits for seconds. So it will display like this, 4 digits. It will go from 000 to 59 minutes 59 seconds. Unfortunately, there is no 7-segment display available for hours, right? So in this lecture, I will explain an example which will count from 000 to 9999. And I will not give you 100% solution. You have to little bit modify it to get 5959. Okay, this is a normal modulo 16 counter. If you just forget about this AND gate, OR gate, and this connection, this CB4RE, you already have seen this. This is a 4-bit counter. In this 4-bit counter, it will count from 0 to 15, then go back to 0 again. And this CEO, you have observed this in the experiment of registers and counters. This CEO will be 1 when it will reach its maximum count, which is 15. Today we will modify it. We'll make it modulo 10 counter. And we'll make our own CEO. Why? Because it will never reach 15. It will go up to 9 maximum. Modulo 10 means 0 to 9. And what is the meaning of modulo? The maximum number of counts this counter can do. Like normally this is called modulo 16 counter. Means it counts from 0 to 15. Modulo 16 counter. But we will modify it to modulo 10 counter. Means it will count from 0 to 9. So what we will do, we'll just connect Q0 and Q3 to an AND gate. Just for a time being, forget about this third input. So when Q0 and Q3 is connected to AND gate, the output of this AND gate will be 1 only when this counter reach 1001, which is 9. Only this situation will make the output of this AND gate equals 1. And this will be as our CEO because maximum count should be 9. So when this counter will reach 9, this output of this AND gate will be 1 at that time. So this is our CEO. And if you look here, this output is going back to, again, just for a few minutes, forget about this OR gate. This output of this AND gate is going back to the reset of this counter. Means whenever it will reach 9, this will be 1 and it will reset the counter. So this will become 0 automatically. So this counter will count from 0 to 9, 0 to 9. And I hope you already know what is CE, what is C. This is clock, this is enable. The CE is circuit enable. When this is 1, this counter will work. When this is 0, this counter will freeze. You have already experienced these things in the lab. So when this is 1, this will count, and depending on the clock, it will count and it will go up to 9. Then it will reset by itself. Now why we have this AND gate and why we have this OR gate? OR gate is very simple. You know that if single input of OR gate is 1, output of OR gate will be 1. So whenever it will reach 9, the output of this AND gate will be 1. And when this is 1, whatever is at the second input of this OR gate, it will reset the counter. Now, for example, it is not at 9, it is at different value other than 9. Then this output of AND gate will be 0. Now we want to reset it manually at any time. So there is a reset input, right? There is a push button here. Whenever we want to reset, this push button will reset it other than 9. Whenever we want, this is like manual reset. Okay, now what is this third input of the AND gate? This is connected with CE. And why it is connected to CE? If you just imagine, that's this CEO is what? This CEO is connected to CE of the next counter if we want to make it bigger counter, another digit we want, for example. So this CE will do what? When this is enabled, it will enable this counter plus due to this one, whenever it reach 9, then this and CE is there, then the CO will be 1. So when this CE is not 1, this will disable this counter as well as it will disable this CO and the next counter. So all the counters in this series will be disabled due to this CE0. Any question why we have this third input for the AND gate? If you have any question, you can put here in the conversation. But while we are in the show, any PowerPoint show, I cannot see your messages. Okay, so let us continue. Now, if we simulate this, this will be the simulation. This is the clock here at the counter and reset in the beginning. We reset it. CE is always 1 and CEO will be 1 only when it reach 9. See, this counter started from 0, 1, 2, 3 up to 9. When it reach 9, this CEO is 1. If you remember, when we tested this counter as modulo 16 counter in our experiment, you have seen CEO was 1 when it was reaching 15. Now it is 1 when it reach 9. Again, when from 9 it will go back to 0. Then this CO becomes 0. And again when it reach 0, 1, 2, 3 up to 9, this becomes 1 again and so on. So after every 10 values, this will be 1. Now, if we want to write, this is the same circuit as in the previous slide. If we want to write the code for this one in Verilog, it will be something like this. Module is modulo 10 counter. And these are the three inputs. Always you have seen this is clock, circuit enable, reset. Here it is clock, reset, CE. And there are 4 output bits, 3:0, and another output, single bit output, CEO. Why we need all the 4? Because we want to see all the digits from 0 to 9. And for this, we need all the 4 bits. We don't need these two output CEOs and TC. So we need all the 4 bits. So 4-bit output and a single bit output CEO. So there is always block, and in sensitivity list, we have positive edge of the clock. Now, if reset, this reset or this CEO, see this OR gate. If reset or CEO is true, counter becomes 0. And it is manual reset or it reach at 9, the CEO is 1 at that time. So this counter becomes 0. Else if CE is there, this CE, and reset is not there, then counter will get the new value, which is what? The previous value of counter plus 1, means it will increment the counter. At every positive edge of the clock, it will increment the counter if CE is there. And this is this AND gate. Assign CEO equals when counter reach 9 and CE is there, this third input of AND gate, CE. So this is modulo 10 counter. Any question?
Yes, doctor. Why I need tab bus tab?
Yes, good question. Nobody asked this question. Here, by the way, this is done by a schematic tool. This is schematic diagram, and that's why we put this bus tab. So if you are doing this experiment using schematic, yes, you need this bus tab. Why? Because we need to feed this to 7-segment display. And if you remember, 7-segment display has 4 inputs, 4 digits, right? D0, D1, D2, D3. So this will go, if it is the least significant, then it will go directly to D0. 4 bits will go to the 4 bits of D0. Understand? But today you are going to do this experiment not using schematic, you are going to do it using Verilog code. Today's experiment is purely Verilog. So here we have these 4 bits, 3:0 counter, output reg 3:0 counter. Clear?
Yes,
Any
clear.
other question? Okay. Now we have seen what is the meaning of modulo. As I mentioned in objectives, we will see what is the meaning of cascaded. This is two modulo 10 counters cascaded with each other. Cascaded means like a train, connected one by one to each other. Like here, you can see this is the modulo 10 counter Verilog code. This is modulo 10 counter schematic diagram. If we just create the symbol of this or this, we'll get something like this. 3 inputs, CE reset clock, and one 4-bit output, which is a counter output, and one single CEO output. So these are the two symbols cascaded with each other. So this becomes what? This is now mod 100 counter. How it will work as mod 100 counter, we will see. The CEO of this is connected to CE of the next mod 10 counter. Clock is common to both of them. Reset is common to both of them. And CE is just connected with the first counter. But if you remember, internally, the CE is connected to the CEO AND gate. Internally, it is connected. Remember, there is a third input of CEO. So this is connected internally. So when this when this CE is 0, it will disable this as well as it will disable this one also, because there is a connection here in the AND gate of CEO. So this will disable this one also. So when CE is 1, reset is not there, clock is there, it will start counting. So what will happen? It will be like this. This is the clock applied to both of them, and reset is initially done in the beginning. Reset was there, then reset is cancelled. So it will work as normal operation. It will do its normal job because the reset is no more there. And CE, this CE is always 1, and this is the 8-bit output, you can say, for count, because this and this both becomes one 8-bit output, any 2 digits. This is least significant D0, this is most significant D1. So both will make a 2-digit output, like here 76, 77. I took this snapshot just to show you both things towards the end of this counter. So look here, after every 10, this CEO1, the CEO1 is 1. See, this is 1. At 79, this is 1. At 89, it is 1. At 99, it is 1. But this CEO, the final CEO, is 1 when the counter reaches its maximum count 99. So this snapshot is towards the end. The CEO was 1 at 9, at 19, at 29, at 39, so on. So here you can see at 79, at 89, at 99, and this CEO is 1 at 99. So this is an example of cascaded modulo 10 counters. Any question?
But in our task, we need from 0 to 59.
Yes.
Yeah,
Yes,
we
you're
do
right.
some modulation in the code, previous code, and we got this output result.
Yes, you are correct. I will explain just 1 minute. I want to see. Okay, Alhamdulillah, everybody looks like here. Yes, good. Okay, now if we write the code for this modular 100 counter, it will be like this. Modulo 100, 3 inputs, clock reset CE, and 2 4-bit outputs. Here you can see D0 4-bit, D1 4-bit, and 1 final output CEO. In this simulation, I just got output from here for demonstration, just to teach you, just to show you. But you don't need it. You just need CEO. So there is a CEO, this CEO, and we are calling this mod 10 two times. Mod 10 M0. I just name it M0. Mod 10 M1, and these are the 5 parameters for mod 10 first counter. These are the 5 parameters for mod 10 second counter. Then N module. In your case, as one of your friends said, you are not going from 0 to 99. You are going to make 0 to 59. So 0 to 59 means here you will have mod 10 counter, and here you will have mod what?
5.
6.
No, mod
Five.
6 counter. You are
Yeah,
Six.
yes, you are correct, but there is a small change. And it will be called mod 6 counter, but it will count up to 5, from 0 to 5. Right? In that sense, you are correct. So it will be from 0 to 5, means 6 different values. So that will be mod 6 counter. And what you will do, you will change it here. Here, just this change. Here, what we are doing, our CEO is what? When it reach 9. In your case, when it reach 5.
5.
So just you have to change here. Counter equal 5. Nothing else. Nothing will be different. Now,
So I need 2 model, one for 9, one for 6.
yes. Okay. Now you can say that this 5, and it will go up to maximum 5. This 5 can be done by 3 bits only. Why we have 4-bit output, right? You can think like this. Because this counter,
Because of the 7 segment.
yes. See, don't make it 3-bit counter. 5 can, up to 5, all the digits can fit into 3 bits, right? But we are going to connect this output to the 7-segment display, and 7-segment display needs 4 bits. So it is like a BCD. If your numbers are whatever, you need 4 bits always. So you must have to put 4 bits here. Don't make 3-bit, okay? Just change the name modulo 6 instead of mod 10, make it mod 6, and change here. Counter equal 5. Nothing else should be changed. So in your case, this will be mod 10, this will be mod 6. Now this is cascaded 3 mod 10 counters just to make it 0 to 999. Now again, there can be one question. What is this question? That if we put here, instead of this counter equal 9, we put here counter equal 99 or counter equal 999, then we can get those counters. Yes, it will do that job, but we cannot display on 7-segment display. 7-segment, as I told you, like a BCD, you need each digit in 4 bits. So that's why we need here 3 counters, not one counter only. 3 different counters to have 4 bits out of each counter. Clear? You don't have to put just one counter of 999. We need 3 counters of mod 10 to make it 0 to 999, means modulo 1000 counter. So it will work like this. This is the output, 3-digit output from 3 counters, D0, D1, D2. D0 is the least significant, D2 is the most significant. So when it will reach 999, then this CEO will be 1. See, this CEO is 1 only when it is at its maximum count 999. Is it clear? Okay. So this is the code. We are calling it 3 times mod 10 counter and 3 outputs of 4-bit each and 1 output of single bit CEO. This is mod 1000 counter. Now here, this is a very important point to be noticed. We can play with the clock also. See here what we are doing, we are providing this clock to all of them together. And the same clock to first counter, same clock to the second counter, same clock to the third counter. So if we are doing it like this, it means all the 3 are synchronized. But we can play with the clock, like if we provide this clock to the first counter and then don't provide the clock to the next 2 counters, what will happen? The first counter will work, and when we want this second counter to be enabled, we can, instead of CE, we can connect clock at this CE input, right? Or keep it at clock and provide the clock at that time only. So this kind of thing will also work, but this will make it all of them unsynchronized. This will not be any more synchronized. It will be like this. In this example, you can see that these are 3 flip-flops. You already know what is a flip-flop, right? So what we are doing, we are providing clock to the first flip-flop, and through the output of this flip-flop Q output, we are providing clock to the next one, and the clock of next one is through the output of this one. So it will do what? Whenever this is 1, it will clock this, it will give 1 pulse to this. When this is 1, it will give 1 pulse to this. But this thing will do what? You know that each circuit have some propagation delay. You have calculated propagation delay of full adder, if you remember, in the experiment number 3. So due to this propagation delay, this clock will be at different time than this clock. So with this red line, you can see that there will be a delay, a small delay. This Q2 will be available after some delay due to this propagation delay of this one. And due to this propagation delay of this one, this Q3 will be more delayed. If there is a fourth one, this delay will increase. So this is like a cumulative delay. So what will happen? That all of these 3 are out of synchronization. Their timings are different. So this thing is called clock gating. Clock gating means there are gates in the path of the clock. Like this is the path, this is clock, then coming from this Q, then this clock is coming from this Q, and so on. So there are gates in the path of the clock. This is not allowed. In some special conditions, you can use it, but this is not a correct engineering approach. It will make everything out of synchronization. Okay, so let us go back to our thing. So this clock is connected without any gate in the path directly to all of these. So all of these are working exactly at the same time. None of this is out of synchronization. Okay, now let us see modulo 10,000 counter. This modulo 10,000 is what? It is calling 4 mod 10 counters, right? And you can see that I did not make the circuit for this. This will count from 0 to 9999, means from, and it is counting 10,000 different values. And there are 4 outputs, 4 bit each, and one single output CO. Okay, now
Dr.
we will
excuse
learn.
me.
Yes,
Can you go to the previous code
here.
for synchronous? Yeah, here for CEO 1 and 2 and 3, we didn't initialize it in our code. So how the code will know which CEO will choose?
Look here. I thought it is not required to explain. See, I named this. I'm going back to mod 100. This
Yes,
CEO, I name it as CEO1, right? So
yes,
here, when I call this mod 10 counter, this one, first one, instead of CEO, I change the color also just to make it
mm,
easy to understand. CEO1, this is the output of this mod 10 counter is CEO1, right?
you're right.
And when I call this mod 10 next one, the CE is what? CEO1. So instead of this CE of this counter, I write here CEO1,
Good.
right? So it means this CEO of first is connected to CE of the next by these same names.
Mm-hmm.
Clear?
Yeah,
Now
yes,
let
clear.
us go to this one. So here this is CEO1, this is CEO2. So these are in correct locations. So this means the CE of this is connected, the CEO of this is connected to CE of this one. CEO of this one is connected to CE of this one. See, only this is the connection between them. Clock and reset are common and outputs are different. So is this clear? Same thing here. CEO of first is CE of the next. CEO of second is CE of the third one. And CEO of the third one is the CE of the fourth one, right? So this is just about 10,000 counter. Yes. Is it clear or any other question?
No, thank you.
Okay, welcome. Now let us see the frequency division. Last time what we did, from this type of fast frequency, we apply a divide by 2 technique using counters to get 1 hertz. Look at the second last waveform, 1 hertz. So it was like this, like a normal clock, 50% duty cycle. 50% duty cycle means in every clock cycle, 50% of the time it is high. And you can see here it is 50% of the time high, 50% time of this cycle is low. This give us this waveform, but not the exact 1 hertz clock. It was almost 0.745 hertz, right? So now today we are going to make a digital clock. This type of frequency will not work over there. We need exact 1 hertz. So today we will do some technique to get 1 hertz clock frequency, but the waveform will be like this, not 50% duty cycle. This is also 1 hertz. If you compare the second and the third waveform, both are 1 hertz, but the duty cycle is different. So how to get this, we'll see in our technique. So this is frequency division from 100,000 to 1 hertz. So how to get this? to generate a signal with a frequency of exactly 1 hertz from 100 megahertz, we need to count the exact number of 100 megahertz cycles that make up a single 1 hertz cycle. So same technique, desired frequency equals 100 megahertz, the available frequency. This is the available frequency at FPGA board, divided by some number x, so that we will get 1 hertz. So 100 megahertz divided by 1 hertz, we will get again 100 megahertz, or 1 with 8 zeros, right? So what we will do, we will write a code for a counter which will count up to 100 megahertz, means from 0 to 8 nines. Understand? If you minus 1 this 100 megahertz, you will get this value, 8 nines. So therefore we need to build a circuit that counts 100 megahertz cycles, then reset back to 0 and start counting again. So this will be modulo 100 megahertz circuit. So it will be like this. We'll get this pulse, this one pulse after every 100 megahertz, and after every 9999, 8 nines. Again, after it will count up to 9999 and 89, it will give us one pulse. But this will be exactly 1 hertz. So we are going to write a code for the counter which will not count up to 9 only. It will be exactly same code, but at the end it will be like this. Instead of comparing it to 9 or 99 or 999 or 4 nines, it will count up to 8 nines. So this will give us exactly 1 hertz frequency. So this is the code, getting 100 megahertz to 1 hertz, and we need a bigger counter, as you already have seen, 27-bit counter to count up to 9999. A 27-bit counter is required. So this is 27-bit counter. So the code is exactly same, only difference is in the name. This is module 1 hertz, and here we have difference. The width is different. It is 27-bit. Remember last time I told you why we are making this width constant type of thing, parameter, because we need this counter so many times. So if we use same code, exactly same code, the parameter will be 27, and output, single output is CEO, single bit output CEO, and rest of the code is exactly same, only the difference is here. Assign CEO 8 nines and CE. So we'll get our 1 hertz from the CEO, 1 hertz from CEO, and this CEO will give us, this CEO will give us 1 hertz frequency, exactly 1 hertz. So when the counter of that 27-bit counter will go to 8 nines, this will become 1. Only at that time it will become 1, like this. Instead of single 9, 8 nines. Whenever it reach 8 nines, this will give us 1 pulse. That will be exactly 1 hertz. So in this way, we will divide our frequency from 100 megahertz to 1 hertz. Okay. Now
This
this is, sorry.
is this modulo 100 million counter?
No. Yes, modulo, but this is just one counter. We are not cascading, right? It is just
But this
one module. We are
is
not
this
cascading.
clock gating?
Yes, this is for the clock.
But this is clock gating, right?
No. It is not clock gating. See, this is what, 4-bit counter.
No, I mean to put the CEO into the clock of the
No.
digital.
Just no. Just I am answering your question. See, this is 4-bit counter, Okay. If this is 4-bit counter, is there any clock gating? No. If we make it same counter, we are not cascading any other counter. If we make same counter of 27 bits, the rest is same. Only this box is 27 bit. Instead of 4 outputs, we will have 27 outputs. Clock will be applied here. We are not getting to anything. It is one counter. So this CO will be 1 when it will reach its maximum count, means 8 nines. Here also we are not clock gating, but this is different thing. This is cascading of 2 more 10 counters.
That's
So
not my question.
your question is, yes, it is clock gating, or in this situation it is clock gating? No, it is one
No,
counter only.
I mean we make this 1 hertz to put it in into the clock input of the digital counter, right?
Yes, now I understand what do you mean by clock gating. Means clock gating between the provided FPGA clock and the clock going to this circuit.
Exactly, yes.
Yes, this is your question. Yes, very good question. Okay, now you are right. It is clock gating, but not this different clock is provided to different circuits in our main circuit. We will divide this one time and then we will provide it to all of the components in our circuit. So all of the components will be synchronized with this clock, right? So this will be available same at the same tick of this clock, and this clock, our 1 hertz clock. At the same tick of this clock, everything will work. So nothing will go out of synchronization,
I see.
right?
So basically, this is now the new FPGA clock for
Yes,
our circuit.
yes, exactly. You are right. So this will be available to all of them. So all of them will get same clock. So it will not be clock gating. Clock gating, yes, you are right. It is in the beginning only. But then every component will get this clock. So it will be okay. Clock gating creates problem when they have different tick of the clock. Everybody will work at its own time, which is asynchronous, not synchronous. So that will create problem. The results are coming at different timings, and then the final output will be wrong. So is this clear? Frequency division from 100 megahertz to 1 hertz, right? Just a simple code you have to write. Okay, now this is the main code. You have to change it to yours. Like here I have mod 10, mod 10, mod 10, mod 10. You have to make it mod 10, mod 6, mod 10, mod 6. Understand? And rest will be almost same. There are 4 outputs in 7 segment display. I'm calling this code 7 segment display. Please, when you submit, this file should be there. Don't make this mistake. And I am insisting every time that please copy this in the project folder. Even then, half of the students did not do that and they did not submit this file. It was
I have a
without
question.
that. It was saying missing when you submit the project. Anyhow,
Doctor, I have a question
inside, sorry,
about the UC. I have a question about the UCF.
yes,
We have the one from the blackboard that's
yes,
named display 7 segment.
yes, that correct. I
We
explained.
rename it into our
No,
project.
no, no need, no need.
Can we have more than one UCF file in our project?
Yes, we can have, and there is other solution also. See, if everybody is listening, I will explain it again. I explained it last time also. 7 segment display is what? It is an output. And you know that for any input or output, we need a UCF file. For 7 segment display, you don't know what are the names of those segments and the anodes. Remember, there are 2 output segment and anode for 7 segment display. So you don't know the name. So we put this in the UCF file of 7-segment display. When you add source this V file of 7-segment, you have to add source the UCF of 7-segment also. Now in this one, you can do two things. One is what? You must need your own UCF file also, like there are some inputs through switches or push buttons, or maybe there is an LED output also. So what to do? You have to create your own UCF, right? So then there will be two UCF files. In one project, two UCF files are acceptable, no problem, it will work. Second solution, if you are now advanced user, not a beginner, you can put just 4 or 5 input output whatever you have in the same file of 7-segment display, and you don't disturb the other things. Just at the end make your own input outputs. This is second way you can do it like this.
And I don't
Sometime
need to rename.
no need to rename. Why rename? It will work with any UCF file with any name. No need to rename it. Another way, just create your own UCF first through IO floor planning, make all input outputs, and then open it in the normal editor. And if you have not included this 7-segment UCF file, it is outside the project, then open it, copy paste all the contents, and you copy all the contents and paste it in your own UCF file. Don't disturb your own bindings. Just at the end copy paste all these contents of 7-segment UCF file. It will work. So there are different ways, but main aim is what? You must have all the connections binding for 7-segment display and all your bindings of your own inputs and outputs. So here in this 7-segment display, this is the clock input. It is same clock. All these clock are system clock. Okay, these are what? System clock V10. And this D0, D1, D2, D3 are the 4 7-segment displays, the 4 digits. D0 is the rightmost, least significant, then D1, D2, D3. Then there are other inputs that you don't need it, and these are the two output, segment and anode. We will need these outputs, these inputs in other experiments. So we just wrote this code as a standard, universal. So if you don't need this input, don't do anything with them. And there are two output, segment and anode, which will be connected to the FPGA 7-segment, right? And you don't have to do anything else with it. It is already assigned in UCF file of 7-segment display. Okay, so here we have 4 mod 10 counters, one 7-segment display code, and then there are 2 different clocks. 1 hertz you already have seen. 1 hertz you got it by what? By dividing it to this value, 100,000. Sorry, 100 megahertz or 100 mega, yani 8 nines. It will count from 0 to 8 nines. That is 1 hertz clock. The output CEO is this 1 hertz. You need what? If you run this counter at a 1 hertz speed, how much time it will take? It will take 1 hour from 000 to 5959. 59 minutes, 59 seconds, right? So it will take 1 hour counting from 0 to 5959. Now, if you want to test your circuit You need 1 hour to wait. So what to do? You can have a higher frequency also, 10 hertz. 10 hertz will be same code, except what will be the difference? Anybody can say?
Just remove 19 from this.
Yes, you are right. Here we have 8 nines. If you just remove one, 7 nines. And you have to write another module 10 hertz instead of 1 hertz. Module 10 hertz. Keep this 27 bit, no problem. But here you should have 7 nines. That will provide you 10 hertz. If you have here 6 nines, it will provide you 100 hertz and so on. So you have to write a code for 10 hertz. Then rest is same, only the CEO will provide you 10 hertz clock. Okay, now here you can see that there is a multiplexer. Single select line means 2 by 1 multiplexer. Output of multiplexer is Y, and depending on this S, if S is 0 and if false, it will go here. It will give you 1 hertz clock. If S is 1, it will give you 10 hertz clock. And this output of multiplexer Y output is connected where? At the CEO of this first mod 10 counter. Sorry, at CE of the first mod 10 counter. Let us go here. For example, if this is the counter, this CE will get this 1 hertz clock or 10 hertz clock. CE, we are not again playing with the clock. Clock is clean. CE, yes, for somebody asked this very valid question that we are doing clock gating. No, in our code we are not doing clock gating. Clock is clean. This is system clock. All are system clock. All are working as system clock. We are playing with this CE. This is 1 hertz or 10 hertz. The first CE. The first CE is running at this output of the multiplexer. Rest is same clock, clock, clock. All are system clock. This is system clock. 1 hertz and 10 hertz. All are system clock. This CLK is a system clock. So,
Okay, Doctor.
yes. Can you speak a little loud?
Okay, it's okay now.
Yeah. Yes. Yes.
Okay.
Good.
Here, why we use like a copy M0, M1, M2, M3 for the module 10, but in 1 hertz and 10 hertz we didn't use a copy.
Yes,
Didn't make a
because okay, very good. Here, as I told you, we are displaying these 4 digits on 7 segment display. So for 7 segment display, our output should not be more than 4 bit. Here in 1 hertz and 10 hertz, we are not displaying anything. We are making this code just to operate these digits, these counters. So this 1 hertz is a 27 bit counter. 10 hertz is a 27 bit counter. There are actually 7 bits output. So we don't need any cascading here. We don't want to display this thing on 7 segment display. This is just a clock source. So we are not cascading this. So we don't need this. Here, as I mentioned, we must have to put 4 bit counters because 7 segment display, each display needs 4 bits. Okay, now,
thank you.
welcome. Now we have this thing. Some student also forget to submit the Word file. Along with the project, you must have to provide the Word file also. So intentionally, I make one more slide here. Next slide, you will see that. Okay, there is one question. You have to answer this question. In the Word file, you have to answer this. What is the question? To check the functionality of circuit at 1 Hz clock speed, it takes 1 hour, right? From 000 to 5959, it will take 1 hour. How much time it will take at the speed of 10 Hz? When instead of 1 Hz, we operate our counter at 10 Hz speed, then how much time it will take to go from 000 to 5959? And the second part of this question, how much time it will take if we operate our timer at a speed of 100 Hz? And how much time it will take from 000 to 5959? So you have to answer this question. There are two parts, part A, part B. And there are three simulations. Do simulation for mod 10, mod 6 and mod 60 counter. Three simulations. In the simulations, you have to show me same thing as I show you here. Yes. See, mod 10 is like this. Some people zoom in too much and just show me the last thing, which is wrong. Show me everything like reset, CE, clock, CEO. So for mod 10, it will be like this. Mod 6, the difference will be here. When it will reach 5, yani this pulse of CEO will be here at the 5. And it will go up to 5. Then after 5, it should be 0, 1, 2, 3, so on. So that will be mod 6 counter. Mod 10, mod 6 is very simple. Mod 60, it will be big. So you can show me in the beginning, one snapshot in the beginning and one snapshot towards the end. When it will reach 59, then it should give this pulse, right? So there will be two snapshots of mod 60 simulation. Let me put here. I will try to change at Blackboard also. Now how to do the simulation? You have to force clock to clock 5 nanosecond, the CLK, and you have to force constant the reset to 1, and then you have to cancel it after little bit more time than the clock, which is like 6 nanosecond. You can make it 7 also, no problem. Then force constant to CE. We always continuously want CE1, so don't cancel it. Here you have the cancel option, and whenever you force constant, a small window will open and it will ask you, you want to force constant to 0 or 1, you have to make it 1. And there is a option to cancel after this time offset. For reset, yes, you can put 6 nanosecond, but for CE, don't put anything. We want CE should be 1 always. And change the radix of the counter in the simulation to unsigned decimal. All of you know how to do this, right? Even I put this. So you have to take the snapshot of all the three simulations. Total there will be 4 snapshots, right? Paste all in the Word file along with the answer of the above question. And what is required? submission through Blackboard only. No email. Don't say I am late for 1 minute or 20 minutes or 10 seconds. This is machine. It will not accept even if you are late by 1 second. So please don't be late. And following thing need to be submitted: a Word file containing answer of the question plus the 3 simulations. And refer previous slide if you don't understand. Complete project. Some students are doing very strange thing. They are just submitting one file only in the project, which is wrong. You will not get any grade of that. Complete project including all code files, all UCF files, then zip or compress it. After doing this, go to project, clean up project files. I mention it every time, but people forget. Today I will show you practically. So project, clean up project file. This will reduce so many files. Then go out of the project folder and right button click and zip it. Some people doesn't know it even. They make exe file and try to send me. Exe file is wrong. And file name should be like this. This time I had a very hard time to find the IDs and names, and everybody submit like experiment 7. So many experiment 7s were there. So many experiment 8s were there. So please do it like this. When you zip it, don't play in the beginning with the file name. Just compress it and then right button click and change the name. It should be like this: experiment 9 underscore your ID number underscore the section number. Right? So it should be like this. Now I will show you demonstration. I try to make it like this. Just I made this video. Okay. Now I will show you the project. This is the code. This is 4 more tens. In your case, it will be different. And this is the multiplexer, 10 hertz, 1 hertz, 7 segment display. Right? Everything is ready made. You don't have to do too much. Even then, You are unlucky if you get something wrong and you submit something wrong, or you don't submit. Allah be with you. May Allah help you. And everything is simple. Nothing you have to do by yourself. Just you have to change mode 10 to mode 6. And 1 hertz is there. Just remove 1 9 to make it 10 hertz. That's all. Nothing difficult. Please don't lose this chance. You will not get grades if you submit something wrong. Everything is very simple. Now look here. Maybe it can zoom. No, it can't zoom. See, I have two UCF files. This is for 7-segment display. This is ready-made, available in the Blackboard. This is my own UCF, experiment 9. Few things, right? I don't want to give you the solution directly. So there are two UCF files. And this is timer file. Inside the timer, there are 4 mode 10 counters. There is a 7-segment display. There is 1 hertz. There is 10 hertz. And nothing else. Yes, any question?
Do we put the Word file in the zipped compressed folder?
It will be nice if you do it. If you can't, submit it along with it. Yes. Anybody else? Any question?
Doctor, when's the deadline for the assignment?
It is tonight, 11:59 p.m.
Could you please postpone it to until tomorrow, because I have major exam today.
Major, online major?
Yes.
How come? I mean, it will be, how they will conduct, they said this?
What?
How they will conduct online?
I don't know. Have GS exam today.
Okay. See, I know that even if I delay, even then there will be students who will say that, oh, I missed the deadline, please accept this through email. Whatever deadline, even if I make it after 1 week, like experiment 7 was after almost 5 days. There were students who said, I missed the deadline, please accept this through email, or just open it again, I will submit. This is wrong. Unfortunately, don't mind it. This is habit of few students. Whatever is the deadline, they will submit after that, which is wrong. Okay, I'll make it tomorrow afternoon. I'll decide the time, but I will announce it at the Blackboard. So I will not accept any late submission. Clear?
Okay, thank you, Doctor.
So if I am giving you the chance, take benefit of this and don't do again same thing, that please accept it, I missed the deadline, and this is wrong. Okay?
Okay, I'll try to do it as soon as possible.
Yes. So any question? Everything is clear? What you have to submit, what you have to do? Everything is clear? Anybody has any question, please ask me.
This lecture is recorded, right?
Yes, it is recorded. And yes, still it is recording.
Okay.
So this will record only voice, I think. I don't know why it is not recording
No,
the screen.
Also the screen.
Last time it was just voice.
We don't know. But in
Okay.
some in other course, it record the screen also.
Let us see. This time maybe it will record. Okay, so anything else you need? Okay. It is,
Doctor,
by the
about
way,
the
UCF
module.
file, not USF file. It is
Can
UCF
I-
file, user constant file. There are two files. One is at the Blackboard. Okay. and one you have to create by yourself. So there are two UCF files. In your own UCF file, you have what? You have clock, you have reset, you have S, the select line for the multiplexer, and CE, circuit enable. And these two are already in the 7-segment UCF file, seg and node. You don't have to worry about this. You have to worry about these four things only. Clock is V10, reset is a push button, S is a slide switch, CE is a slide switch. Clear? Any question? Is it clear about UCF file?
ان شاء الله.
And this is for the 7-segment display. And there is one for experiment 9. Yes, Mishal, is it okay? Okay, so do you need anything else? Okay, now we will close the session. I will be available at email. Send me through email any problem. I don't think there will be any problem. Everything is very simple. But please submit correct thing. Don't submit garbage. And some students are not submitting all the files, just one file, which is wrong. I need whole project. And how to do this, I will show you here. Go to project, clean up project files, right? Project, then clean up project file. It will delete all of these unwanted ones. Click OK. And now see here. Again, go there, project, clean up project file. No file is there. So many files are deleted. So do this, then go out of this folder, like here, right button click and compress. Okay. Don't make exe file. Just compress it and submit at Blackboard. Any question? Okay, so should I hang up?
Yes.
Okay.
Yes.
So please submit on time, and if you have any problem, send me email. But no submission through email, only Blackboard. I will extend the date up to tomorrow afternoon, maybe 4 o'clock. Okay. See you then.